I'm going to do now is, there's a process called PolyMumps. All right, I'll take your question. Just give me a second. PolyMumps. And it's a more general process. It's one of the most important topics in this class. So I'm going to spend my time. It's about 20-something steps. But hopefully you get them, okay? Now, I'm not going to blame you if you don't get everything right now. That's why you go to the clean room and start, correlating both and start making sense out of this, okay? Lady over there had a question, yes?
Which layer was the poly one? Was that the following?
The green one, yeah. So the orange one was poly 0, and then the green one was poly 1.
And poly 2 is the...
Poly 2 I did not cover it. Now I'm going to cover it. Okay. Okay, just to show you essentially the process I talked about so far. And we've done it not in our lab, and we did a design. When I joined this university, I gave you the context. We did not have a clean room. So if you are in a university where they don't have a clean room and you want to teach people about these kind of processes, so the industry came out, actually not even the industry, before the industry actually, the MEMS community came up with this very innovative, now before the shared abide and all that kind of, you think that shared economics is only millennia thing? No, in our time we have the shared MEMS thing. So what it meant was, if you want to do MEMS, and you don't have a clean room, so somebody who has a clean room will define a process which is standard. Maybe 3 layers of polysilicon, maybe 2 layers of metal, 1 layer of what you call sacrificial layer, and then they say, okay, if you follow this design requirement, and then you do the design on conventional ware or any of the layouts, and send it to us, we're going to be blinded to the actual design. So we're going to run it through our process, you're going to get a device. And then we're going to cut the, from a wafer, we're going to cut the dies, 1 centimeter by 1 centimeter, or 1 inch by 1 inch. We're going to send it to you. So that was the first shared kind of economics in MEMS, but that came in the early 90s. So I want you to understand this. So in the early 90s, a lot of universities did not have clean room. But we needed to train people who are, I think I mentioned this. In fact, if you look at the largest manufacturing industry, it's semiconductor industry. Global, okay? So we need to train people who know these kind of things. So the only way to do that was at least train them how to do the design and all that, let it be fabricated somewhere else, and then you bring it and you do your, you use it yourself. So, like I said, even as DSU, the first 1 and 1.5 year, I used the same thing. So we graduated a number of people. So this was one of our designs. So we have poly 0 at the bottom. So this is poly 1 with the dimple and all that kind of stuff. So we send it to the external vendor and it comes back to us. So even now, a lot of big public universities, even private universities, do not have clean rooms. Very expensive to maintain. So they still use this one, okay? Right now, in fact, they are running, and I'm going to show you the slide, we are doing run 118 or 128. 128. So they do about 4 of these, or 5 of these, okay? Now, it's very possible you could join a startup company, or you could join even a big, large company. If they want to do design, in fact, when I was in the industry, I even consulted with General Atomics, I remember, many years ago. So they wanted to send stuff to this, and so even the large companies, if they want to go through this, they will have to use this. Therefore, it's important that you learn about this process, okay? Now, you may not remember everything, but at least getting through the whole thing, the whole steps will give you appreciation. Okay, given that, PolyMumps is a very important lecture. So, what I'm going to do is I'm going to review the so-called MUMPs. MUMPs stands for multi-user. MEMS process. Okay? Now, if you're using polysilicon, then it becomes PolyMumps. If you're using, there's something called silicon on insulator, SOI, so it becomes SOI MUMPs. If you use just metals, then it becomes metals mumps. Okay? So there's a company in the East Coast, North Carolina Research Triangle area, which does this. Anyway, we're going to cover the process, and then I'm going to give you what we're going to look at the example which we did today. In terms of reading, I want you to read. I don't know if this website is still up, memsaras.com. They had a very good article that still carried, MEMS thin film deposition processes. So that's the additional reading that you have to go after my lecture. Okay? So that will give you a better understanding. The Century and Maru was additional references. Okay. Of course, you've seen this today. This example. So what I'm going to do is, and then this is one of the first commercial accelerometers. Yeah.
What did the S in MUMPs stand for?
So process system or something, I forgot. Multi-user MEMS process
System.
No, it's not system. I forgot. Yeah. Anything? Another question? Not the same? Oh, you guys are so curious. Even one letter I can't skip. Okay, very good. I'm used to just saying stuff and getting away with it. No, I know what I'm talking about. Yeah, word processes, but well, sometimes. Yeah, you know the problem with mum. It's a disease, right? Yeah. Who wants? So who wants that? Okay, so MUMPs, the multi-user MEMS process. They've been running it since the 90s, and I'm going to show you a slide. I think, like I said, they do about 4 of these every year. If you're doing polysilicon, it's very common, PolyMumps. If you're using piezo material, they have one specifically for piezo materials. So that's piezo mumps. And there's something called silicon on insulator. It's a very thick silicon. That's SOI. And then metal mumps. Now, the way it works, I already explained. So you buy a real estate. So they have a 6-inch. So they run their process on a 6-inch wafer. So what's going to happen is they give you, typically, so you have to break this. So typically they give you 1 inch by 1 inch. Die, that's going to die, okay? So what's going to happen is, there are going to be, I think when we do, by the way, we have one class for Coventer with tutorial. And that time actually we're building the whole wafer. And then because you're going to understand some of these terms. So we have what we call dicing lanes or dicing path, because what's going to happen is once you make this 1 inch by 1 inch parts, eventually you have to cut them. And there's a dicing saw. It's a diamond saw actually. So you take this guy, it's already programmed, and it comes in and it breaks them into this 1 inch by 1 inch section, okay? So essentially what you're buying is this guy. 1 inch by 1 inch is cheap. It's, I think you get it about a couple of hundreds of dollars. So you could get 4 of these for about $2,000. Sometimes when you're really short on money, which I was at one point, so I contacted them, and then they contacted me with this guy who works with the Air Force Lab. I don't even know him. Said, yeah, I'm going to give you in the 1 inch by 1 inch, 0.5 mm by 0.5 mm. Things were very difficult that time. 0.5 by 0.5 mm, then they dice it and they send it to me, so he gets the remaining. So it's very innovative. I mean, they work with you in terms of budget and so on. So the way it works, I know their process, which I'm going to explain right now. So based on that, there is a mask. Now, when we do Coventer work, you're going to appreciate it. There is a template that you're going to pick every time. And when you do your final design project, you're going to use this template. That's why I'm covering it today, okay? Now, the program actually has most of this already inside. They have names like with Dimple, Anchor 1, Anchor 2, Layer 1, PSG, whatever. So, all that is going to be tied to this, okay? So from now until the end of the semester, as far as this class is concerned, all these things are going to be tied to this, okay? Now, so they process it, and then typically it takes about 12 weeks after you send your mask, and then about 12 weeks time, then you get your chip. Now, in fact, that gives you an idea. It's a very expensive process in terms of time. I mean, you could do a lot of things in 3 months, but actually the process takes that. Takes that long. So that's why before you actually finalize your design, you do a lot of simulation. In no other discipline, and I want you to pay attention to this. I mean, there are many disciplines where you don't even do simulation. You do a mechanical design, and then you build your stuff. I'll say electrical car racing or the old IC. I mean, you do a little bit of simulation, but most of it, by instinct, you could do it, and then stuff works. Not here. You mess up with a small design, 3 months are gone. Then you correct that, who has that kind of time? So beforehand, you have to do a lot of finite element simulation, fluid mechanics, solid mechanics, whatever it is, and then firm up the design, and then eventually you send it. Anyway, yes?
These simulations, do they normally take into account like the scaling factors? Like, is there specialized simulations, or
They-
can you use like anything really?
So 2 types of simulation. One is the finite element simulation, right? So how much voltage do I need to move this thing? What's the spring constant that I want? For example, accelerometer. Typically, I want my frequency, right? The first frequency is k over m, right? So this is an approximate way, but if I'm designing an accelerometer for 1 gigahertz of frequency, then you have to prove that. So what you do is you do a finite element model for that, and then show that you can get 1 gigahertz. If your customer says, okay, I want 1.25 gigahertz, but with a bandwidth of this much, you don't design and build and then test it. So you do a simulation. Now, I'm trying to get this Coventerware guy to come and show you a new tool. So he's been trying to sell it to me. I mean, we already have it. We have the license. But I never use it. But you'll be surprised. Like I said, there are 2 types of modeling. One is mathematical based. The other one is actually model based. Then you define the process, and it's going to give you, in fact, almost like a real life looking chip model. And it's going to handle how it's going to cut it in 40, 50, 60 degrees, whatever. If you make a mistake in the process, that modeling tool actually shows you how you're going to mess up. If it's going to be washed away, for example, if you didn't design the anchor very well, it's going to get washed away. So I'm trying to get the guy here as a visitor. I really would like you to see that. Okay? But anyway, when we say modeling, that's what we mean. Okay, now let's get into, so you can read this thing by yourself. So, like I said, 3 types, PolyMumps. I have 3 polysilicon layers. Poly 0, Poly 1, Poly 2, and 2 oxide layers. The first PSG as a sacrificial layer, the second PSG as a mask, hard mask. And then we're going to have a metal layer and then a nitride layer, the nitride insulation. We're going to come, I'm going to come back to this, but you have 1, 2, 3, 4, 7 layers, okay? But a number of steps. The other ones are SOI, piezo bumps. You don't need to know about them. If you want to read, you can read. Okay, this is a little bit old. I looked it up, the recent one today. Like I said, they are on run 128. So in February, they just did 129th, and in the summer, they're going to do the 130th. So it really shows you how popular it is. But if you've got the numbers, PolyMumps is more popular than the others. These are highly specialized. Not everybody does PS. Okay, now, this is the scary one. But you're going to find out it's not that big of a deal. At the end, once we're done, what I want you to do is review this. So we'll come back to it at the end, okay? And you just have to see, okay, look. I have an oxide layer, a nitride layer, and a poly 0, a PSG. You already know. If you see a 2 micron over here, it looks like a sacrificial layer. That's my PSG layer. And this guy is an anchor. You can already see the anchor. And this green guy is another poly layer. And that's a metal layer. So at the end, that's what's going to look like, okay? It doesn't make sense right now, so we're going to come back to it at the end. In fact, the color codes are given here. But just to give you an example of the kind of devices that were built, usually a lot of accelerometers or motor. Actually, like I told you, if you go to YouTube and search for MEMS motors, you will see the Sandia product. Again, it was done by the same process. This is an accelerometer. Samsung Galaxy has these kind of accelerometers, radial accelerometers. Most of Apple's accelerometers are the linear accelerometers. So they have the X, Y, Z. And then from version to version, they change. I remember iPhone 6 or 7 had an accelerometer, triaxial accelerometer, or X, Y, Z, all integrated. And then they came back and they say, no, I don't know how this thing happens. But they said, okay, now we're going to separate the X, the Y, and the Z. And then they said, oh, no, we need one more set of accelerometers. So you have the high frequency accelerometers and the low frequency accelerometers. So iPhone 10 has about 6 or 7 of these accelerometers. Okay? But typically, as far as Apple is concerned, it's mostly linear kind of configures, but this is a radial. Some of the Samsung ones have it. And this is another set of structures like mirror. If you're very clever, and one of the reasons I like MEMS is in terms of the challenge that you have in terms of design mechanisms. So, a 2D process, how can I build 3D structures? Origami type of structure. There are people who have done origami kind of structures, they open out. Or gear kind of structures. No, hinge type of structures, I'm sorry. And this is actually a micro mirror which opens up. Okay? So in terms of the kind of clever design that you could do. In fact, in this, has anybody done machine design? Yeah, everybody's quiet. It checks out zone UCI, which means machine design. And the reason is because there's one guy. Now, once he dies, of course, machine design dies. So I remember teaching that course once, UCI, Joseph Sabato. Because most of these are kind of specialized, right? But for me, and some of you have taken my other courses will know, design is where really the excitement goes in engineering. I mean, quality, we have mortgages and we have to pay and we need a job, right? But really engineering is when you do design. And then clever ones, especially, you're limited by the process here. It's only two-dimensional. But how can I build this guy? Remember, when this guy was built, it was two-dimensional. But if you design it in such a way that maybe it's pre-stressed and then you remove the stress and it comes actually kind of bounce up and you get this 3D kind of structure. Okay? So we'll try to see if in the final design project I can push you that way. You're going to hate me, but maybe in a couple of years. Good luck. But anyway, now, this is the final structure. Let's see how we build it. Stay with me, 15-20 minutes, intense. You start with silicon substrate. In PolyMumps case, this company called MEMSCAP in Research Triangle, they typically use 150 millimeter, which is 6 inches, okay? Silicon wafer, it's 100, homework number 1. Does anybody remember what 100 is? Remember, it was cut only in one direction, like the X or the Y or the Z. Yeah, the Miller indices. So you start with that, with some kind of resistivity. Then the next thing that you do is the black one. I think you asked me. For example, this one we don't use oxide, actually. And PolyMumps, yeah. Let me make a correction on this one. So that version that I showed you was out of Berkeley, Bill Tong's, Bill Tong. His design where he used oxide as well as nitride. PolyMumps, just nitride. Okay? Now, but they do the doping to get excess of N+. So you take the silicon substrate, the 100, you dope it with phosphorus until you have excess of N++ to prevent the penetration of the electrodes. Okay, the electrons. Prevents charge feedback, yeah. Then what you do is you deposit 600 nanometers, 0.6 micron. So this is what I want you to do. I was playing with this. Oh, I forgot my note. I don't want to do it over here. So let's define this one. So when you take a note, it's going to help you. So you're going to have a layer, then it's going to have a mask, and then let's say thickness. What else do we need to do? Thickness and then maybe process. And then miscellaneous. Okay? So we're going to build this as we go. But I'm trying to think, what's going to help you to not just memorize this thing, but at least get a feel to it, okay? So the first layer is nitride. We don't use any mask. Thickness, 0.6 micron, right? And the process is LPCVD. So you guys remember LPCVD stands for low pressure chemical deposition. Then, that's used for insulation. Then we deposit our first poly layer, which is poly 0. So layer name here is going to be poly 0. Thickness, it's very thin, 0.5 micron or 500 nanometers. Process LP CVD. Okay, so far so good. Then we pattern it. Okay. Now let me put this patterning. So patterning is, of course, lethal. And then if we have miscellaneous, we put miscellaneous. Okay. Now, the first layer nitride, we don't need to pattern it because I'm going to cover everything with nitride. Okay? So no patterning. Poly 0, I'm going to pattern, but using, SU8 or whatever. Well, no, not SU8, Shipley or whatever. So we're going to just call it photolitho with Shipley. Okay. Yeah, with the photoresist actually. Yeah, instead of Shipley, actually, let me be generic with photoresist. As opposed to the KSG. Okay, everybody with me on this? I know some of you may not be able to see this. Any questions on this, folks? Yes.
Poly 0, that was the insulation that was like doped.
No, so the insulation is nitride, right?
Yeah.
So, the wafer itself, you're going to dope it with phosphorus because you don't want charge to feed back to it. In addition, you put a nitride there. Then once you have that, then you start putting poly 0. Now poly 0, remember I told you guys, that's where I'm going to build my wires, where I'm going to talk to the electronics. So, yeah, so that's the, so when I pattern it, I'm going to pattern it into wires and all that kind of stuff. Okay? All right, we got poly 0. So, then I put the photoresist because I want to pattern my wires. Okay? That's a photolitho that's captured with this in the table. Okay, then, so essentially that's what it says. Using an appropriate mask, they expose peons, develop coating, all that kind of stuff. Then you get figure 2. Remember, when you do a litho, you did the photoresist, you put your mask, so apparently there was a dark one over here, transparent, no. So for this guy to remain, it has to be dark, yeah. Positive litho, remember. So positive litho, so this guy remains, the other guy is taken. Now, what? So based on this, what do you think is going to be following? Remember, the photoresist is for protection, for mask. So what do you think is next?
You're going to
Edging. So I'm going to edge the red guy, poly 0. I'm going to pattern. So that's what happens here. I do poly 0 edge, poly 0 edge. Now, there is a mask. The mask name is you don't need to worry about this now, well, not much, but in a couple of weeks, you will be worrying about this. Now, remember I told you guys, I'm going to put you in a group and one person is going to be in charge of a conventional wear, and one person is going to be in charge of simulation. So the person who's going to be in charge of conventional wear is going to have a lot of acid reflex actions, and it's going to be very stressed out, okay? if they're not systematic, okay? So some of these layers are named already in the software. So those of you who aspire to be the Coventerware people, pay attention. That's why I'm putting them as green. But now, all I want you to know is there's a mask called PolyZero. I mean, it's easy actually. It's going to be a mask which has that feature. Okay? All right, now, what do you think is the next step? I got my PolyZero, it's patterned. I'm ready for the next level. PSG, right? The first oxide. And you can see it over there. And to answer your question, the gentleman at the back, now remember, whenever you have something at the bottom and then you're depositing on top of it, it's going to assume a shape like that. Of course, it's going to be a little bit curved, but it's a cartoon, so I'm going to make it straight. Okay? So now I have the first oxide. I'm going to call it, yeah, let me use their terminology. So it's going to be first oxide, but we know it's PSG. Okay, how thick? 2 microns. So 2 microns PSG. What's the process that I use for depositing PSG? Again, LPCVD. Under miscellaneous, one thing you want to add is it's going to be annealed. Okay? So under miscellaneous, put annealing for 1 hour. Annealing means because it's, when you combine a high temperature process with a room temperature process, you're going to have a mismatch. So you want to slowly raise it to 1,000 degrees Celsius, anneal it for a couple of hours, bring it down, then the stress is kind of distributed. Otherwise, you're going to have all this kind of shriveling kind of action. Okay? Remember, this is run number 128. So they have gone through all this and then figured this one out. Okay? All right, so annealing is very important. All right, so we're getting there. What's the next step? Poly 1. Remember, we're C programmers, so we don't start from 1, we start from 0.
Is that really why they call it PolyZero?
Some nerds. Okay. Now, actually, there's one thing. Before Poly 1, I forgot about the dimple. So we're going to have a dimple. So it's not really a layer, but I'm going to have this intermediate layer. Intermediate process, dimple. So what I'm going to do is I'm going to do one litho, which will give me a dimple. Now, dimple is a subtractive process. So under the miscellaneous, just put subtractive process or subtraction. Remember, we're not adding, but we're subtracting. We're doing something, okay? So I really want to catch that. So you're going to use a mask called dimple. Let's write it in green. And how much material am I going to take? About 0.6, 0.75. Okay? And I'm going to use RIE, so the process, because it's a subtractive, I'm going to put a minus in front of it. Okay? Any questions? All right, so you guys are with me. Now, I think I'm ready to add Poly 1. So, Poly 1 comes in, it's the gray one. I don't know if everybody could see that. So, you have the first oxide, and on top of that, you put Poly 1. Poly 1 is also 2 micron thick. Okay? So, I'm going to put Poly 1, 2 micron thick. Typically, LPCVD. I'll be surprised if they change equipment and then use something else. Imagine if you are in production kind of stuff, you want to keep the same process, right? Okay, so of course there was something I missed over there, but don't worry about it. There's also anchor. Remember that question that we had? Well, so we did the dimple, and then I started cheap. Yeah, after the dimple, we have to do the anchor also. So there is still one more process after the dimple. If you want, you can add it. because I'm running out of space over here. But right after the dimple, you could put anchor 1. Again, the same thing. Instead of 0.5 micron, it's going to be 2 micron because you're going to go all the way through the PSG. Okay, now, just to make this point, I don't want to confuse you. So, I did my dimple, so that was the first figure 5. But I also needed to prepare an anchor. So I'm going to do anchor 1 etching. Again, it's a subtraction process. So another series of lithography on that, and then get. Yeah. Okay, so at this point, you deposit your poly 1. The poly 1 will go through the anchor, and it will go through the dimple structure. And in a cartoon way, it's going to look like that. Okay? Now, here is where it becomes important. I want to pattern poly 1 because it's 2 micron thick, as I explained before. The patterning is going to be PSG, litho with PSG hard mask. So to make a distinction between the two types of masks, the type of masks. Remember the mask that I showed you? Let's call that soft mask. Okay? Now, hard mask is the mask that you deposit to help you etch through things. Okay. It's getting a little bit complicated, but we're almost there. Okay? We have only 2 more layers. So at this point, I put the PSG mask because I'm ready to pattern poly 1. Otherwise, poly 1 is covering the whole wafer. It's useless, and that's not what I want. I want to break it into what you call accelerometers or whatever, gyros, whatever the need is. So at this point, I do a litho. First on the PSG mask, make openings here, right? Then etch through that. So at this point, poly 1 is etched. And if you remember, this guy is going to be part of your anchor. What do you think is going to be this guy? Or these guys? Homework number 2. That's going to be part of the proof mask, right? And then at the other end, that's the anchor. So you have 4 anchors, and in between you have the proof masses and then the figures. So the figure is going to be part of this guy. Partly figure, partly anchor. Does it make sense? Okay. All right, almost there. Now, I have only 1 more layer, metal. But before I do that, then I create a second oxide. So I'm going to call it second oxide. So a second oxide, 750 nanometers, so 0.7 nanometer. Micron. Now, if you don't have time to, you can take a picture at the end if you can't see it. Then you can prepare it on your own leisure time, okay? But I think for understanding this process, doing your own version is important instead of just memorizing whatever I do, okay? Now, it gets a little bit complicated about this P1, poly 1, and poly 2 via, but don't worry if you don't get it, but let me tell you what it is. It turns out, sometimes I want, because I'm going to deposit 1 more layer of poly. I want poly 2, the third polysilicon layer. I want it to talk to poly 1 sometimes. Sometimes I want it to talk to only poly 2, or no, poly 1. So in that case, we came up with this mechanism where, remember that the word via? If you speak Spanish, then you know via. But it's via means through. Okay? Now, I have 1 more process to make that opening, vertical opening. So I'm going to connect only poly 2 to poly 1. So I'm going to do that thing here, which opens up all the way to poly 1. Okay? The same thing over here. If you don't understand it, don't worry about it, because not all designs have that need. Okay? So typical designs are, you have poly 0 and then poly 1, and then you're okay. You don't need poly 2. And you don't need poly 2 to talk only to poly 1 instead of poly 2 talking to poly 0. Okay? So if you're following me up to step number 4, that's okay. The brave ones, I encourage you to read this. Okay? Now, I have done my second oxide because I was going to do this weird stuff. So at this point, I have these guys exposed. Poly 2 doesn't necessarily it's of course going to be a different layer than poly 1, so I need another superficial layer. So oxide 2 is actually a superficial layer, okay? So it's a negative. Okay, now, hopefully the last process, yes. So at this point what happened was I did the additional weird thing, which is I wanted to come all the way to poly 0, because I told you poly 2 needs to talk to poly 0, so in that case I'm going to have an anchor, so I opened that, anchor 2. It's also possible that I just need access only to poly 1, I did that thing, okay? And that's what the second oxide did. Once I've done that, I'm done. Okay? So you could call this process the nerd process, because not everybody needs it. So if you follow me up to poly 1, I'm okay. Now, at this point, all I need is a metal. It turns out, most of the use was for micrometers, very reflective surfaces. Poly 0 is not reflective. So what we're going to do is, on top of the poly layer, we're going to put a metal there. Well,
How is it that you etched through the second oxide layer only in the middle once you had already taken the protective layer off the poly 1 on the side?
since you asked, so essentially you're saying how do I get access only to this guy, right?
Yeah, how do you break down the middle without touching the sides if you've already broken down the layer?
No, what do you mean? So we're talking about, I have two steps. One step is I cover this guy and I do etching all the way here. And that's based on the timing.
Yeah.
If my etching is about 10 micron per half an hour, then I could calculate and I could say, okay, this is how much I need, then I'm going to expose this. Then at that point, strip out everything. It's just like the way I did dimple plus anchor, right? Then strip out everything, so then you cover everything. Now, all this is covered except this guy.
Okay.
Now I come in and I do DRI on this.
Okay.
So that's why I call it the nerd layer. Yeah.
So when you're doing that kind of etching, depending on how deep you need to go, you might have to do 1 or 2 masks to kind of
Yeah,
like it.
yeah. So that's why I really, at this point, I don't want to confuse you too much. I just want to make sure at least up to poly 1 you understood me. But then when you want to go deeper, then there are additional things that you have to do. Okay? Yes?
So in the example, the one that's for the homework, you have a dip in the lower layer below the dimple, but in this one there's not a dip below.
Yeah, I'm not a cartoon and different design.
Okay, so usually there is a dip for the dimple.
Depends on how you want to pattern, right? So let me see where poly. Actually, that's a good question. Let me see in this particular cartoon if I'm going to have that dip. Yeah, well, no. I have that. Well, yes. So remember, I have this opening, right? But it turns out I don't have any feature on top of that. So the way I designed it, so I kept it that way. But if it turns out, my wire is right below this guy, then when this guy is deposited, then you're going to have that kind of dip. Okay? So that's confusing, probably. I mean, I should not have that dip in the other structure. But anyway, that was taken from a different design. Okay, now. So that you could follow me now. So the last point I was explaining was we put our metal. But before we put metal, we have to pattern poly 2. So you're going to put poly 2 here. I'm running out of space, but poly 2. Now poly 2 is very similar to poly 1. 2 microns. You can see it. It's very deep. If you want to pattern that, you cannot use just a photoresist. You have to use a hard mask, PSG. So you do your PSG. That's what you see the dot, the loop. Once you do the PSG, you do lithography. And then you're able to pattern. Okay, now we're almost there. Poly 2 is patterned. Yeah, 21, it's figure 14. Yeah, well. Yeah, so at this point, I have my Poly 2. The only thing remaining is metal layer. I do metal deposition. In fact, I ran out of space again. Last step is metal. And you could, as it's sputtering that metal that provides. So, metal is sputtered. So on this table, so typically for metal, the layer is going to be about 50 nanometers. Okay, but somebody asked me about adhesion. Where was that you or something? Did you ask me? About metal layer?
Yeah.
So typically with metal, it doesn't, yeah, the typical metal that we use gold. Gold does not attach to things very easily. So what you do is you have an adhesion layer, which is chrome. So I want you to remember this. So whenever you want to deposit gold, first deposit chromium. You need adhesion. Chromium will attach to anything. And then gold loves chromium, so you could come in and put gold on top of chromium. Now sometimes we want to do platinum instead of gold. So typically we use a normal metals. Now platinum, again, does not stick very well to anything. So what you do is you use titanium, Ti. So let me write that one out. I don't want to be sidetracked from this, but titanium and platinum go together. And chromium and gold go together. And these guys are adhesion layers, typically 10 nanometers. And platinum and gold by themselves are at 30 to 40 nanometers. Because they're expensive. So our platinum target, we paid $17,000. Oh, I should have kept quiet. It's expensive on the market. So gold target is, depending on the market, sometimes it's 20 grand, it's just 4 inches, right? So you cannot deposit a whole micron. It's very expensive, so you want to keep it for about 2-3 years. So that's why, you want to be limited within that range. Okay, at the end you have your metal, so the only thing remaining is getting rid of the oxide. Oxide 2 gets washed away, oxide 1 gets washed away. Then, voila. You get this cartoon. Very similar to homework number 2. So you have an anchor which is on that side, remember, which is supporting the beams. And the proof mass, again another anchor here. Poly 1 has its dimple and all that kind of stuff. So the process in general looks like this. 3 polysilicon layers, 2 oxide layers, and 1 metal layer. All right, congratulations for surviving